Today, climate change is considered one of the most critical threats to biodiversity. High-latitude ecosystems, such as the Canadian boreal forests, are predicted to experience abrupt climate-induced changes, which may reduce the total forested area by almost 42%. Boreal birds are susceptible to both direct and indirect effects of climate change, and several studies have predicted northward shifts in species distribution as the climate gets warmer. These shifts, paired with a potential ecozone contraction, may lead to decreased abundance of many species as habitat shifts and climate gets warmer. My research is evaluating projections of bird densities on integrated models of climate change and forest dynamics in the taiga plains within the Northwest Territories from 2011 until 2091. I show a figure of the study area in the lower left corner of this poster. We identify the winners and the losers over the short and the long term, and we evaluate the spatial variation in responses among three contrasting general circulation models. For doing this, we had predicted densities for 72 bird species for the current 2011 and the future 2031 or 2091 time periods. We put these predicted density maps into the spatial discrete event simulator to get the simulations of climate change and forest dynamics under three contrasting general circulation models that were chosen to represent the minimum, the ENM-CM4, the average, CCSM4, and the maximum, CAN ESM2, of projected changes in mean annual temperature and total annual precipitation over the study area. The future climates were evaluated under the representative concentration pathway RCP 8.5, which may be considered the worst but most likely case scenario of climate change for 2100 based on the continuation of current policies and economic incentives. For each of the GCMs and species and time period, we have 5 replicates. For each having all these replicates, we calculated the mean density across all replicates, and we calculated the predicted abundance by multiplying the predicted density per cell by the grid cell area, which was 6.25. After that, we sum all the pixels and we obtained the total abundance. We evaluated the impact of climate change on predicted bird abundance in the short, from 2011 until 2031, and the long term, from 2011 until 2091 for each of the selected GCMs. After that, we calculated the proportional change in predicted abundance by dividing the abundance on the time period we were interested by the current abundance or abundance in 2011. Given that the values of abundances or densities were too high and contrasting for some species and too low for others, we converted the predicted density values to probability of occurrence in order to exemplify the magnitude of change among GCMs more homogeneously. We used a species-specific density threshold to define the historical identified high density areas in the study area. We consider a winner those species that their population size increased by at least a factor of 1.5, and a loser those species that decreased by a half. Some of the results that we have for the short-term period is that few species show early responses in at least one GCM. Within the winners, we have the olive-sided flycatcher, eastern kingbird, varied thrush, and the red-winged blackbird. And among the biggest losers for this time, it's the gray-cheeked thrush, white-crowned sparrow, American tree sparrow, fox sparrow, and one white-winged crossbill. In this figure, the lower part, we are seeing the spatial changes within the study area, and we observed the decreases in the were mainly in the high subarctic ecoregion, and representing the most conspicuous losers for this time frame. And as you can see, the white-winged crossbill has the major decreases for CCSM4. For the long term, we have 9 species that show an increase in their predicted abundance by a factor of 1.5 consistently among GCMs. In these graphs, we have the long-term predicted abundance under the 3 GCMs. Again, maximum, average, minimum, or temperature and precipitation, and the diagonal slope represents the one-on-one relationship. Everything above the green line is a winner, and everything below the red line is a loser. As you can see in this poster, there are more winners, more species that were considered winners and losers for each of the GCMs, but the pattern of winners and losers kind of continue through the long term. Again, we have the eastern kingbird, the red-winged blackbird, the brown-headed cowbird, and some other species like alder flycatcher, song sparrow, red-eyed vireo, etc. And among the winners, again, we have way more species, but among the most conspicuous losers are 4 species of sparrow: the white-crowned sparrow, the American tree sparrow, Lincoln sparrow, and fox sparrow. Again, in this picture, we have the spatial distribution or spatial changes for 2 winners and for 2 losers. And the eastern kingbird, as well as the red-winged blackbird, have their increases in the low subarctic ecoregion, while the decreases for the gray-cheeked thrush and the white-crowned sparrow occur in the high subarctic ecoregion. From this, we can conclude that in the long term, populations of more or less 48% of the species increase in at least 1 GCM, that certain groups of species show decline, including sparrows and some thrushes. Species showing major declines include both rare and widespread species, and bird species in the northern latitudes are showing early responses to climate change. In the short term, to 2031, 9 species declined in at least 1 GCM. Most of these declines were in the high latitudes, and these species can be considered bell ringers. Thank you very much for your attention. I just want to say thank you to Université Laval, the Western Boreal Initiative, the NSERC Alliance project that financed my research, the Boreal Avian Modeling Project, and of course the Space Predicted Ecology Lab.